Hello, everyone. Welcome to today's live broadcast, Avoiding the Pitfalls when Automating Cell Viability Counting for Biopharmaceutical Quality Control. I am Brenda Kelly-Kim of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter. Beckman Coulter develops, manufactures, and markets products that simplify, automate, and innovate complex biomedical testing. Our products are making a difference in people's lives by improving the productivity of medical professionals and scientists, supplying critical information for improving patient health, and delivering trusted solutions for research and discovery. For more information, please visit www.beckmancoulter.com. We have a few announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit your questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many of your questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of your presentation window or submit your problem through the green Q&A button, lower left. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, please click on the CE button located in the bottom left-hand corner of your web page and follow the process for obtaining your credits. I would now like to introduce today's speaker, Tony Harrison. Tony held the convenership of the ISO Working Group revising ISO 14698-1 and -2 for microbial control in clean rooms and is the UK subject matter expert to the ISO Working Group, currently revising ISO 14644-1 and 2, as well as manufacturing chapters of both the European GMP and the USA CGMP documents. Tony holds a bachelor's degree in electrical and electronic engineering and is employed by Beckman Coulter Life Sciences as a senior marketing manager. Tony was joint editor on the ISPE Guide to Ozone Sanitation of Pharmaceutical Water Systems and was also the chief editor for PHSS Best Practice Guide for Clean Room Monitoring. He is a well-known international speaker and has provided educational seminars on TOC, liquid particle counting, ozone sanitation for water systems, and clean room monitoring in UK, France, Italy, India, Malaysia, China, the US, Scandinavia, Ireland, Hungary, Switzerland, Indonesia, Belgium, Greece, Switzerland, Turkey, Denmark, and most recently, Scotland and Poland. I will now turn it over to Tony Harrison for his presentation.
Hello, my name is Tony Harrison, and I work for Beckman Coulter. Thank you for the introduction. I appreciate that. So today I'm going to be talking about common pitfalls when automating cell counting and how to overcome them using the ViCell automated Trypan Blue cell counter. Today's presentation is in three parts. During the first part, I will explain the ViCell counter technology, how it works, and how it compares to the manual Haemocytometer method using the Haemocytometer and a microscope. In the second section, I'll describe some of the common pitfalls that can lead to discrepancies in results when switching from either the manual Haemocytometer and microscope method or from an old automated cell counter to a newer automated cell counter. And thirdly, I will explain how to avoid these pitfalls using the ViCell automated cell counter. Now, I should say that there is no right or wrong way when you're counting viable cells. People do it differently, and the whole point of this presentation is to explain how the ViCell can be adapted to avoid those common pitfalls. So let's take a look at the automated cell counter technology in the ViCell counter. Both the European and the United States pharmacopoeias have chapters on cell viability counting. Both recommend a dye exclusion method for identifying viable cells, and both of them suggest that Trypan Blue is a suitable dye to use. So the cell sample is mixed with the Trypan Blue dye, and the cells that are healthy repel the dye, whereas the cells that are dead are stained by the dye and they go dark. And it's the difference between the white, clear cells and the dark, stained cells that tells us which ones are viable and alive and which ones are dead. So it's a standard method recommended in both the European and the United States pharmacopoeias. And the Vicell simply automates this standard dye exclusion method using the Trypan Blue. Traditional cell counting was done using a slide counter, which was originally designed to count human blood cells, hence the term Haemocytometer, hemo coming from the word blood. It's a very manual and error-prone method requiring a very high degree of skill to obtain repeatable results. The Trypan Blue addition is done manually, so it's pipetted into the cell sample, and the mixing of the dye and the sample is also a manual method. Once the sample is mixed and the slide is put under the microscope, the identification of viable cells and dead cells and the counting of them is done manually. Then, because the sample size on the Haemocytometer is so small, the count then has to be multiplied by a factor of 100,000 to obtain the viable cell count concentration in counts per milliliter. So we're converting nanoliter sample size here to milliliter sample size. So you can imagine any small errors that are made during the mixing, the addition of the Trypan Blue, or the counting of the cells are multiplied by 100,000 when you're trying to take that count up to counts per milliliter. So the Vicell automates the Trypan Blue dye exclusion method. It uses an imaging technique to simulate the counting by the human eye. So the Trypan Blue is added as usual, it's mixed, and then the Vicell uses a very high resolution camera to identify which cells have been dyed and which cells actually stay nice and white and are actually viable. So the Vicell has two independent steps it follows here. The first one is sample preparation, where it mimics what a technician would do by hand if they were using a Haemocytometer. And then the second section is the actual sample analysis. During the sample preparation step, the sample is drawn up from the beaker and it's aspirated a number of times. Of course, if we leave cells in a sample for a period of time, they tend to settle out. So this aspiration process is really important, and it can be adjusted in the Vicell to match the same process or same procedure that you would follow if you were doing it manually. So this aspiration process resuspends the cells in the sample and aims to make the sample homogeneous. A controlled amount of Trypan Blue is then added, and this addition is metered, so it's a very accurate addition, and the sample is then mixed a number of times to ensure even mixing of the cell sample and the Trypan Blue dye. The mixed sample is then sent to the measurement cell in batches. As each batch enters the measurement cell, a high-resolution picture is taken using a very high-resolution digital camera. The software then interprets the images that it sees and reports total cell count and total viable cell count per milliliter. It can be adjusted to take between 1 and 100 different images, so 1 to 100 different samples can be analyzed using this process. So statistically, it's a lot higher chance of having a correct concentration when it reports this compared to the Haemocytometer method, which only takes nanoliters of sample and a single image. So this is the Vicell main analysis window. The Vicell retains each sample photograph for future reanalysis. Healthy, viable cells are identified by the Vicell by circling them in green on the screen. Whereas you can see here some of the darker cells in the picture are identified as dead, and these are circled in red. In this way, the user can see exactly how the device cell is interpreting the picture it sees and identifying and counting the cells. On the right-hand portion of the screen, the device cell presents the analysis results. The right-hand column on the right-hand side shows the analysis results for all the images taken, so between 1 and 100. And you can see at the top left there of the image, it says camera image 52 of 100. So we're looking at the picture 52 of sample 52. And it's on the left-hand column on the right-hand side there, it says image 52, and it reports the cell counts and the viability percentage and total cells, etc. for this particular image, counts per milliliter. The user can scroll through each individual image and check that the device cell is interpreting the cell counts just as they would do if they were using a haemocytometer or a different process to count cells. So you can scroll backwards and forwards and see exactly how the device cell is doing it, and then adjust the way the device cell does it to match your own. So let's take a look at some of the common pitfalls associated with automating cell counting. The manual haemocytometer method delivers inherently variable results between cell counting technicians. It's a very manual process, and it involves very accurate pipetting skills. Remember, we're looking at nanoliters here, nanoliters of sample. And so if the dye is added incorrectly or in an incorrect volume, then we will affect the results per milliliter calculated when we multiply it up. The identification of live and dead cells is also subjective. From a study involving 16 cell counting technicians, results on viable cell concentration would seem to be varied by plus or minus 20%. And you can see why this would be. It's nothing to do with the skill set of the technicians. It's just there's so many different manual steps in this and opportunities for error. Please excuse me a second. Here we go. So the identification of exactly what a healthy cell looks like is the third area where variation creeps in. In an attempt to avoid counting cell debris, in the same as if it was viable cells or dead cells even, some technicians will only count cells as being viable if they are over a certain size. So they look for large, healthy cells and ignore the smaller ones. Other technicians will only count sharply outlined cells and not fuzzy cell images. Cell viability is, of course, as I discussed, decided by the absence of the Trypan Blue dye from the cell itself. However, the white area in the center of cells will differ from different cell types, and interpreting the limit at which a cell is characterized as dead may vary from operator to operator and from sample to sample. And of course, when we're in the manufacturing environment and we're taking samples from the larger bioreactors, the drive for ever-increasing yield from those cells is driving the population density. It's getting more and more concentration of cells per milliliter. And this, of course, increases the likelihood that cells will start to clump together. Now, some users, when they're analyzing these cells, decide not to count individual cells, but rather to count a clump of cells as if it was just one cell. And they do this to try and avoid the variability of interpreting how many cells there are in that clump, whereas other people try to identify each and every individual cell in the clump with varying success, of course, and this is another area of variability. And of course, finally, not all cell types are conveniently round, and so this makes it difficult to differentiate between dead cell debris or the cells themselves. Even an automated cell counter can enumerate cells differently between the different manufacturers. So take a look at this automated cell counter here. It's now obsolete, but it was a very common model. It uses Trypan Blue. It has a relatively poor resolution digital camera, and the new model, which is brought out to replace the obsolete model, has a much higher resolution camera, which arguably gives it a better accuracy at cell counting. However, the high resolution camera, combined with a slightly different sample preparation and analysis methods, means that it reports a different cell viability concentration on the same sample when compared to the old model. Poor resolution in the old model means that it does not reliably identify dead cells, and it's not very capable at counting individual cells in a clump. The new model, however, has much higher resolution and can better identify dead cells and count individual cells in a clump. However, the result is, of course, that it gives a different cell concentration on the same sample compared to the old one, and this makes it very difficult when you swap into the new counter. In fact, the key to selecting new automated cell counter is the precision of the counter. Counters with low accuracy and low precision will, of course, inherently give varying sample results. Equally, automated counters that are able to count close to the correct results but have high sample-to-sample imprecision are not good either. What is required in a new automated counter is a counter that can be adjusted and configured to interpret the cell counts in the same way as the old method that you used previously, i.e. it should count the cells in the same way that you would. So on the two targets on the right-hand side of the screen, you can see we've got all of the samples analyzed and giving the same results very close together. So you've got good repeatability there and high precision. Now, on the lower target, you can see all of those are in the center of the target, but on the top left, you can see they're all clustered over the top left of that target. Both of them could be correct. It depends on how you have you're previously counting. So if you've got a high resolution counter, it may be that getting them all in the center of the target is not reproducible and compared to what you were doing before. So you need to be able to adjust the way the counter counts to make sure that it reproducibly counts in the same way that you would have done before. So one of the common pitfalls when you're switching to an automated system is cell size. If we take a look at this view from the ViCell, the counter here has been configured to include every cell that looks viable, nice strong white center, and has a diameter of 6 microns or larger. And you can see it's identified the cell arrowed on the screen, which actually has a cell diameter of just 8.1 microns. And it's telling us this is a viable cell, and it's circled it in green. Oops. Right. Sorry, my apologies. You can see the reported viable cell concentration for the sample is 10.73 times 10 to the 6 cells per milliliter. Now let's take a look at what happens when we adjust the cell size that the analyzer identifies as viable. If we adjust the minimum allowable viable cell size to 15 microns or larger, so if you remember in the previous slide it was set to 6 microns or larger, so now we're changing it to 15 microns and larger. So you can see that the counter no longer circles this cell in green, and so it's saying this one is no longer a viable cell. And you can also see that the reported total viable cell count per milliliters changes to 7.23 times 10 to the 6 cells per milliliter, whereas before it was reporting 10.73. This is a reduction of almost 33% from the previous slide. So you can see how slight variations in the way that viable cells are counted and included according to the cell diameter can have a significant effect on the reported cell viability count per milliliter. Another common pitfall is the interpretation of cell clumps. In this slide here, you can see that the automated counter has been set to count each and every cell and identify them as viable in clumps of viable cells. You can see that the reported concentration of viable cells per milliliter is 10.53 times 10 to the 6 cells per milliliter. In this next slide, we've adjusted the automated counter settings, so it now counts clumps of cells as if they were just one single cell. And the impact on the reported viable cell concentration is huge, dropping the reported concentration from 10.53 down to 8.85 times 10 to the 6 cells per milliliter, which is a reduction of 16%. This slide shows the counting window of a relatively low-cost automated counter. It's got very poor resolution, and you can see on the screen here that it's counting 2 cells which are slightly clumped together as counting them as just one cell and identifying them as just one. So you can imagine from this, the results from this low-cost automated counter may vary significantly from the way that you yourself would count cells. As I say, this is becoming particularly important as the cell concentration in the large bioreactors in production is getting higher and higher. So we've taken a look at the typical pitfalls, or some of them, involved in switching to a new automated cell counter. Now let's take a look at how the ViCell automated cell counter can help you overcome them. Now remember, there is no right or wrong when it comes to counting cells. It's just reproducing the way that you've done it previously. So when it comes to selecting a new automated cell counter, the ability to adjust the way that the new counter counts so that it mimics and counts the cells in the same way that you do with high precision is the most important aspect. As standard, the ViCell comes configured to provide 8 standard cell counting configurations which cover the most common cell types, such as Chinese hamster ovary or CHO cells. These can be fine-tuned to match the way that you would count these cells, and also it can be programmed with new cell types. These can be created and stored in the ViCell memory should you wish. So if you're sampling different types of cells, you can just recall the configuration from this memory. So to avoid the common pitfalls, we recommend that you follow this process. First, analyze a sample of your cells using the current method that you're using, whether it be a Haemocytometer and microscope or some other type of automated counter. Secondly, analyze the same sample on the ViCell. Thirdly, utilize the ViCell file type adjustment feature to configure the ViCell and the sample preparation settings to optimize the ViCell so that it counts the cells the same way that you would. The ViCell records all of the images from the counting, so adjustments can be made and the same set of images can be reanalyzed as many times on the screen as needed to optimize the ViCell to your particular technique, or to match the other technique of some other automated counter that you've been previously used. So you can adjust it and then reanalyze the cells to see how the adjustment affects it. The cell type feature allows you to adjust the cell counting parameters by cell diameter, cell brightness, viable spot size, viable spot brightness, cell sharpness, and minimum cell circularity. You can even adjust the way that the ViCell counts cells in a clump to best represent the way that you would do it. In addition, the number of sample aspiration cycles can be adjusted, and the number of Trypan Blue mixing cycles can be individually configured to match your practices. So for example, some people, when they're using very delicate cells, will reduce the number of aspiration and Trypan Blue mixing cycles to avoid damaging the cells and killing them. So whether you're moving from a manual cell counting technique using a Haemocytometer slide and a microscope, or simply looking to replace an old automated cell counter. By fine-tuning the ViCell, it can be optimized to report viable cell concentrations to support your process. So that's the end of my presentation today. A short presentation, but hopefully I've communicated well to you. If you need any information on this particular analyzer, you can find it at www.particle.com or www.beckmancoulter.com. Thank you very much for your attention.
Thank you, Tony, for bringing us that informative presentation. Before we get started with our question and answer session, I do want to remind our audience how to submit their questions. Questions can be submitted by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to get to as many of your questions as we can today, and we do already have some. An attendee asked, does this system have 2 or more cameras or only 1 camera for visualization?
Okay, so this is just a single camera. It uses a high-resolution digital camera. I don't understand quite what the reason for the question was, but it's a bright field camera, so it's just a single camera.
Okay, our next question. Does the ViCell distinguish viability of cell populations of different volumes within the same sample, for example, blood?
Sorry, can you run that past me again, please?
Certainly. Can the ViCell distinguish viability of the cell populations of different volumes within the same sample, for example, within blood?
Okay, so I think the question is about the volume of the cell size itself. So if you have mixed populations of different cell sizes within the sample, and I believe that's where the question is coming from, can the ViCell actually count the cell viability? Yes, it can. Basically, when you're setting the minimum cell size, you have to make sure that it encompasses the smallest cells you've got in your sample as well as the largest cells. But for sure, if you've got a mixed population of cells with different sizes, the ViCell will work perfectly well. You can just configure it and it will count the smaller cells and the larger cells and identify them as viable.
Great. Our next question, do we need to buy software for this machine?
Yes, you do. The software I was showing on the screen here, I'll put this one I'm showing you here, runs on a PC. So yes, the ViCell instrument itself handles all the automation, the aspiration, the addition of the Trypan Blue, the mixing, and then it pushes the images past the camera and the camera captures the images, but the information is analyzed by the software. So it's the software that you change the configuration to make it match the way that you would do the counting. So yes, there is a separate software package. And in fact, all of the images, you can configure it so it saves all the images from the run for future reanalysis. So if you ever have some questions from a particular batch of cells and you want to go back and reanalyze the images, you can pull them back up from the memory into the software and reanalyze them on the screen.
I see. I think we have a clarification of an earlier question. An attendee says, for clarification, if I understood, we have in this system 8 programs for 8 types of cells, CHO, hybridoma, etc. And what do we do if we have another type of cells? Is it a flexible system?
Right, okay, I understand. So yes, for certain. So as standard, it comes with pre-configured to count a certain number of the more common types of cells that we would see. As I mentioned there, Chinese hamster ovary is or CHO cells is a very common type of cell which people use. So it comes with those pre-configured in there. So there's a number of them, as you can see on the screen now. I've gone back to that slide. So we've got the CHO cells in there. We've got yeast cells, etc. So it comes with a standard set, which is, in our opinion, the best way to count those cells. However, two things. First of all, the way that it counts those cells and the way it counts those individual cells can be adjusted. So you can adjust, for instance, the way that it counts the CHO cells by cell size or circularity or whatever parameter you wish to do, so that it matches more closely the way that you would count CHO cells, and then you can save that. So every time you pull up the configuration for CHO cells, it matches the configuration that you've configured it to. And then you can actually add additional configurations. So if you have a different type of different type of cell that you're using, you can start from scratch and completely configure it to match the way that you would count those cells and store that in the counter. So yes, it's very user configurable. That's really the basis of what I was trying to communicate today, is that you can configure the counter to count the cells the way that you would count the cells, whether it's using a Haemocytometer or using a different automated system. This can be adjusted to match that. Absolutely, very configurable.
I see. Our next question, if certain cell types are particularly clumpy, would it be worth increasing the number of Trypan Blue mixing cycles? And if so, what is the maximum number of mixing cycles?
Yeah, so certainly, certainly if you have a very clumpy sample of cells, well, these cells tend to clump, then there's two things you can do on here. One is the actual number of aspiration cycles can be adjusted on the screen here. You can see we've got aspiration cycles. Get it listed there. We are aspiration cycles, and then below it we've got Trypan Blue mixing. So both of them can be adjusted to help to break those clumps up. The only issue you might find is, of course, if the cells are a little bit delicate, then as you increase the number of aspiration cycles, then it can actually potentially harm the cells themselves and break the cell walls. So it's a trade-off that the instrument is adjustable. You can adjust it to match your normal technique, or you can adjust it to actually try and break those clumps up. As I mentioned, the combination of being able to adjust these and also to be able to adjust it to the way that it actually declusters or declumps those. You can see on this screen here at the bottom, we have the decluster degree. We're asking there the device cell to identify either individual cells in a clump and try and count them, or to ignore them and count them as one single lump. And I think, yes, this screen here, you can see at the top left, you can see it's got a clump of cells and it's identified them as one. Whereas if we change the way the analyzer works, you can see on this screen here, it's a little bit difficult to see, but it's identified each and every cell in the sample, in the clump, as if it was an individual cell, and counted it into the bi-cell counting. So, yeah, it's user configurable, basically. You play around with it to match whatever suits your particular samples.
Great. Our next question coming in, why is Trypan Blue used specifically? Can we use another dye in place of Trypan Blue for cell viability?
For sure. And I guess today's presentation I was kind of focusing on the biopharmaceutical industry for research and also manufacturing. And the reason typically people use Trypan Blue in that industry is because the pharmacopoeias, both the European pharmacopoeia, and I'm showing you on the screen now, the chapter in the European pharmacopoeia and the United States pharmacopoeia, both of them actually mention Trypan Blue by name. Ironically, they don't mention any other dyes, and there are other dyes that can be used, but because typically, of course, it's a regulated industry, people tend to follow exactly what it says in the rule books, and the rule books say Trypan Blue. So, but certainly in other industries, like the brewing industry, they use different dyes which are more suitable for their applications and their cell types. So certainly you can use different dyes. The Vicell is designed to work with Trypan Blue only and to automate that method. So if you wish to use other dyes, the Vicell is just designed for Trypan Blue because it's designed for that industry.
Okay. Our next question, what's the minimum and maximum cell concentration range acceptable for Vicell?
So this will go up to 10 million cells per milliliter. And we're finding that some people are trying to push above that, and the way around that, of course, is to dilute the sample. So without the beauty of this is you don't need any manual addition or mixing with the sample. You can just take the sample, put it into the carousel, press analyze, and the Vicell does it all. So it takes out all of the variability in the analysis, which is, you know, it adds a metered dose of Trypan Blue. It always aspirates the same number of times. It always mixes the Trypan Blue the same way. So, and the way it interprets cell viability is always done exactly the same way. So it removes all of the variability. I'm sorry, I've lost where I was with the question. Can you repeat it, please? I apologize.
No worries. The last question was, what is the minimum and maximum cell concentration range acceptable for Vicell? Sorry.
Yeah, got it. Thank you. Right. So 10 million cells per milliliter is the answer to that. It can sample down to 5 million cells per milliliter and even lower. But of course, once we start going lower, the number of cells that we see on the screen are very, very, very small. So, for instance, in one application, I saw they were counting very small concentrations of cells per milliliter. And literally, each of the images that came across the screen on the Vicell, there'd be like one cell in the screen, and that's it's fine, and the Vicell will handle it. But of course, statistically, it's not very sound because, like the Haemocytometer, the actual sample analyzed is quite small. So any errors in the sample analysis are multiplied up when we take it up to counts per milliliter. So it will, it'll count individual cells per image, no problem. You've got one cell per image, it'll count. But statistically, it's not very sound. So for the higher end, people can dilute. The sad thing is, of course, you're adding a manual step into the process, which is not the idea. But yeah, so I hope that answers the question for you.
Okay. Our next question, going back to a previous topic, what can you do to guard against clotting of cells?
Okay, so that's unfortunately it's a little bit outside of the scope of the presentation today. I don't have an answer for you. I would suspect it varies depending on the cell type you're using and the concentration you're trying to achieve. In this particular case, we can't influence that for you. Some people will actually go for a specific media type that they're growing the cells in, which tends to help them reduce the clumping. As I mentioned, on the way that the analyzer analyzes, we can configure the way it analyzes the number of aspiration cycles it does, which gives you helps to break those clumps up. But at the end of the day, if you have a particularly clumpy type of cell, there's not much we can do to stop the cells clumping. As I mentioned here, we can just adjust the aspiration cycles and the Trypan Blue mixing cycles to try and break the clumps up. And then the fact that the analyzer does have a declustering or declumping feature when it's doing the measurement, so it'll try and identify individual cells within the clumps anyway. So those two things combined can help. But unfortunately, if you've got clumpy cells or cells that tend to clump anyway, there's nothing we can do with sorry, my apologies. There's nothing I've seen which specifically would help with that, unless you can change the media a little bit to try and discourage the clumpiness.
Great. Lots of questions today. Our next one is, can this machine be approved by the FDA yet? Is it FDA approved? Can it be used in clinical testing like CD34 testing?
Okay, so this machine is not approved for clinical use. It's really designed for research and development when somebody's developing cell lines. It's used in cell banks, and it's used in production quality control in the GMP environment. So it is it is used in the GMP environment. It's not used in the clinical environment, and it's not designed for the clinical environment. So if you were doing blood testing, for instance, in the clinical environment, then this is not the machine to use. So it's not FDA approved for that application.
Okay. Our next question, for high throughput counting of high numbers of cultures, is it possible to insert a 96 well plate into the machine?
Not yet. We are currently going through our next stage of the development with this instrument, and so we hope to have new analyzers coming out in the not too distant future. Certainly not this year, but in the not too distant future, and that's certainly one of the considerations we are taking into the new designs. But currently, this just takes individual cups.
Great. Our next question, is it possible to automate the counts of various cell populations within a single sample?
Oh, I see. Okay. Right. Yeah, I think I understand what the question's about. So if you have a mixture of different cell types in the particular sample you're trying to analyze, can you fine-tune the VICE cell to, I think the question is saying, can you differentiate between the cell types in the sample using the VICE cell? You can't. So on the screen here, for instance, I've got the cell type optimization. You can see the different parameters. We've got cell diameter, et cetera, et cetera. That's a single configuration for the VICE cell. You can't have it identify different cells differently in the same image. It's just a single one-off.
Okay. Our next question, does the VICE cell have high throughput screening capabilities to count multiple samples at one time?
No, it does not. It takes each individual sample in, it mixes the Trypan Blue in, et cetera, then does the analysis of that sample. There is an auto sampler on the front of the analyzer. Let me just get a picture of it up, which will allow you to put multiple samples in and then walk away. You can just see here at the front of the analyzer, there's a little auto sampler carousel here, but it's not designed for high volume screening, no.
Okay. Our next question is about the software. Does the software have an audio trail, meaning tracing of the growth curve in case of audits?
Yeah, so you can configure it so that you can add multiple samples over time and to give you a growth curve with doubling times and things like that. So it'll so you effectively, as each sample related to that particular growth curve is added into the VICE cell, you pull it up and you tell it, right, this is another sample from the same this is the same sample from the same set of cells as they're growing over time, and it'll add the cell counts, etc., into that record, and it'll give you a graphical trend, and it'll give you doubling in time, etc., etc. So yes, it can give you all of that in the software.
Great. Another question. How big is the footprint of the machine?
Well, it depends who's asking that question, but if I'm speaking in American terms, it's about 14 inches square on its footprint, something like that. For those of you who speak in centimeters, I would say it's about 34 centimeters square in the footprint, approximately.
Okay. Another question. What is the lowest acceptable cell density the VICE cell can measure accurately? Tony?
Sorry, my apologies there. That's the kind of a how long's a piece of string question, because it depends on how statistically sound you want your results. So I have seen people using it literally for single cells on each slide of the pictures and images you see on the screen in front of you. But of course, the statistical sound, that's really not very good. So really you do need fairly high concentrations, and we would suggest somewhere around 500,000 cells per milliliter and upwards.
Great. Our next question, how is cell circularity defined in the Vi cell? Activated T cells can start having pseudopods. So how does the Vi cell still count this?
Okay, so in the Vi cell, let's bring that slide up. Here you can see at on the left-hand side, the second to the bottom there, it says minimum cell circularity. So you can adjust the way that the counter counts the cells, so it can either look for a perfect sphere, if you like, well, as near as perfect as possible, or it can start to look at elongated cells. So you can adjust the way the Vi cell does that according to the cell types you're counting.
I see. Okay, let me just check our questions. And I think that is all we have for questions, but before we go, I'd like to just throw it back to Tony for any final comments or advice that he might have for our attendees today.
Thank you. I think the key message I was trying to say today was, as I said, there isn't a right or wrong way to count the cells and identify them, and that's what's key when you're trying to automate cell counting. It's trying to have a cell counter which allows you to vary the way it interprets the images it's seeing and counts as closely as you would do if you were doing it yourself using the Haemocytometer or using an older type of automated cell counter. So it's very important to be able to configure it to do that. And the Vi cell itself, as I mentioned, as it takes these images of the cells and does the analysis, it stores the images. So you can go back in again, you can actually take a look at how it does the cell counting, how it's interpreted viable cells and dead cells, and you can adjust the way it does and then reanalyze the same set of images again so that it gets closer to how you would actually count the cells, and you can compare that to your previous method. So that was the main message I was trying to give today, and I appreciate everybody's time today. Thank you for attending, and thank you for a very interactive question and answer session.
And thank you, Tony, for bringing this important information to us today. I also want to thank our sponsor, Beckman Coulter, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through October 2016. You'll be receiving an email from LabRoots alerting you when this webcast will be available for replay. And we invite you to please forward that announcement to your colleagues who may have missed today's live event. That's all we have for today. We hope we see you next time, and goodbye.